Okay, so welcome you all to the morning session. Today's first speaker is Shreyasi Datta from University of Michigan, and she will be talking about p-adic Diophantine approximation with respect to fractal measures.
Thank you so much. First of all, I want to say happy birthday to Professor Dani. It's a great pleasure to be able to present my work here. I also wanted to mention that Professor Dani was one of my PhD examiners. So some of this work, like one part of what I'm going to say, he already saw. And okay, so as my title suggests, that I'm going to talk about p-adic Diophantine approximation. So let me first talk about what QP is. So it's just, so if you have set of integers, you can always define this p-adic norm, which is that if A is p to the power k m, where p does not divide m, then you can define the p-adic norm of A to be just p to the power minus k. And you can define a p-adic norm on rationals as well. And then you can say that QP is just completion of Q under this p-adic norm. Okay, so is my writing readable?
Yeah, it is readable. Maybe you can write slightly bigger.
Okay, and please feel free to ask me any question if you have. Okay, so what do we know about this space QP? So here I tried to draw a part of Q5. So we know that this is a totally disconnected space. Moreover, we know that the metric that we have here, which is the p-adic metric, is actually stronger than the Euclidean metric, which is, so if I take x plus y p, then it should be less than maximum of. Okay, so what do we mean by p-adic Diophantine approximation? So just like Q is dense in R, Q is also dense in QP, since QP is a completion of Q. So you can think about numbers in Q as, I mean, they are just P by Q. So you basically approximate X in QP by P by Q. So I should not again use P. So let's say Q naught. Okay, so there is, so in case of p-adic Diophantine approximation, and even in case of real Diophantine approximation, you can always think about rationals as Q naught by Q, where you can take Q naught Q from Z. And also you can think about Q naught by Q, where Q naught and Q are from Z 1 over P. So in today's talk, at some point, I'm going to talk about approximating points in QP in these two kind of manners. Okay, so let me start with the Dirichlet theorem, since we know that Q is dense. So QPN. So let's say X is in QPN. Then in fact, let's take X to be in ZPN. So this is the unit ball in QPN. And then for all large enough Q, capital Q, you can always find non-zero integer solutions to Q dot X plus Q naught, p-adic norm less than equal to 1 by capital Q to the power. In this case, it would be n plus 1. And the height of the rational will be determined by Q and Q naught both. So it would be Q and Q naught, their infinity norm less than equal to capital Q. Okay, so what is the difference? The difference with real numbers, real vectors, is that here the power should be n plus 1, which makes sense because you are taking height. The definition of height involves both numerator and denominator. So that's why you should have, instead of n, you should have n plus 1. And why is it that the height is determined by both Q and Q naught? The reason is very simple. So since we know that Z is dense, so Z is dense in ZP. So instead of taking what I wrote before, if you just imitate the real case and just take Q dot X plus Q naught, let's say, and then the height, let's say you determine just by Q, then you can actually just fix Q and take Q naught to be whatever you want, and then you can actually improve this power to infinity, meaning you can do it for any power. So that's why that kind of Diophantine approximation would not be interesting. That's why the height should involve both Q and Q naught. Okay. All right, so since we know Dirichlet's theorem in case of QPN, the next question is that what about variable approximable vectors, which means which are the vectors for which you can improve the Dirichlet exponent. So I should first recall what some of the previous works. So I'll start with a work of Mahler in 1940, where he started. In fact, it was around 1935, where he started working on p-adic Diophantine approximation. And you can look at this paper titled as On a Geometrical Representation of p-adic numbers. This is kind of the starting point. And then you can, since you know Dirichlet's theorem, you can also talk about Khinchin type theorem. So Khinchin type theorem in QP was proved by Yarnik. It was sometime before 1950. And then for higher dimension linear form, this previous work of Yarnik was extended by Lutz in 1955. Okay, so these are the classical results, and there are more which I'm not mentioning. And then Sprinjuk, then comes what happens for submanifolds. Okay, so so Sprinjuk in, I forgot, it would be around 1965. So they proved for both R and QP Mahler's conjecture. So let me write what it is. Probably most of you already know the conjecture. So for lambda 1, so lambda 1 is a Lebesgue measure. So it's just the Haar measure on real line. So lambda 1, almost every x, any vector on this higher dimensional parabola would be almost every is not variable approximable. Okay, and this result was in case of inhomogeneous Diophantine approximation. So I'm not going to talk about inhomogeneous, so I'm not defining it, but it's just in the linear form, you can add one extra term. So you can add a theta, and theta, you fix theta, And if you vary Q and Q naught, and you can still ask same kind of questions. So an inhomogeneous version of the Spin-Jukes results were proved by Barnick, Dickinson, and one, and this was in 1999. And I also want to mention that there are recent results and past results by Bujo and others. So I'll write only 2 papers, but there are many papers by them. So and these are also for points in this kind of curves. Okay, so the first one is, let me write 2. So this was in 2011, and then there is a recent work by Badzian, Badzian, Bujo, and slides since. So they basically, so like we can talk about dual different, so we can talk about linear forms, but we can also talk about approximation from lines. So you can talk about simultaneous Diophantine approximation. So they, in these 2 papers, they study the simultaneous exponent, which they denote by lambda n. And so they study lambda n for vectors on these kind of curves. Okay, now let's go back to Spin-Juk conjecture. So we know the so we talked about Mahler conjecture, which was proved by Spin-Juk. And then in I think it was in 2000. So it was by Beresnevich, and Kovalevskaya. So they proved Khinchin type theorem for both convergence and divergence. So both convergence and divergence. And they proved for curves like this, where x comma f of x, where f is normal function, such that f double derivative is not 0 for almost every x. So in particular, they also proved that all of these curves are not, has this property that variable approximable set has measure 0. Okay, so since I'm going to talk about again and again about the set of variable approximable points
What is normal function?
Okay, so normal, you can just think about analytic, but it has more restriction. Okay, any other question? Okay, so these was last work that I mentioned was in 2002, I guess, I believe. And then in 2000, so around the same time, Kleinbock and Margulis proved the Spin-Juk conjecture, which is that, so this was in 1998. And this was in RN. So I'm not getting into very technical details. So I'll just write the, this is not the most general result that they proved. So I'll just write that F is a map from an open subset of U, open subset U of RD to Rn. And let's say F is real analytic. and let's assume that f is not flat. You cannot have any neighborhood where f is inside any affine hyperplane. So then the set of variable approximable has measure 0. So I'm going to write f star lambda d of VWA is 0. Okay, so right, and this was conjectured by Sprinjuk in 1980s, which Kleinbock and Margulis proved. And the two ingredients that they used, one was Dani's correspondence, which we have seen many times in this conference. And I'm going to talk a bit about that later. And the second idea is to extend Dani's quantitative non-divergence. Okay, so now that we know this, the next question is when can we replace f star lambda d by any other measure, or like what are the right conditions on any let's say Federer measures such that the same thing happens. Okay. So let me write it down. So what are the measures mu for which mu of VWA has measure 0? And this question is valid for reals and for QP. So here comes the result in 2002 or 2004. I forgot the exact date. So this is by Kleinbock, Lindenstrauss, and Weiss. This is in 2000, okay, 4 or 5, I guess. Sorry. Which says that if mu is friendly, which I'm going to define in a bit, then it implies that mu has this property. So I don't want to say that same thing again and again. So I'm going to write this property as extremal, or that's what people generally call it. So if mu satisfies this property that the variable approximable has measure 0, then you call mu to be extremal. Okay. And I also want to mention a recent work. It's not that recent. It's in 2016-17. And it's by these 4 authors. So they prove a more general condition, which I'm not going to define here, but you should, if you are interested, you can look at the definition. So they say mu is weakly quasi-decaying, then mu is extremal. And this is a weaker condition than being friendly. Okay, all right. So since I'm talking about friendly measures, I should define them. But before that, I should mention that this Kleinbock-Lindenstrauss-Weiss result that mu friendly implies that mu is extremal was also considered in case of QPN. And this was done by Kleinbock and Tomanov in 2007. And we are going to use this theorem, Kleinbock-Tomanov's theorem, later. Okay, so let me try to kind of give an idea about friendly measures. So for that, I need to define something called absolutely good or good maps. But you can think about polynomials with respect to Lebesgue measure. It's basically sort of functions for which if you take the piece where you have the function has very small value, then that set should also have small measure. Okay, so a good map with respect to mu. So in this whole talk, mu is always going to be a Federer measure. So I'll define what Federer means. It means a doubling measure. Okay, so let's say G is a map from QP D to QP QP, and the definition of good map you can define over any field. Okay, so is a C alpha good on U? U is an open subset of QPT. If you take any ball, so let's say this is your U, and you take any, sorry. If you take any ball inside U, and then you look at all x in B such that G of x is less than epsilon, times, let's say, the essential supremum of the function with respect to mu, then that should be small. So that should be less than C times epsilon to the power alpha mu of B. So that is the definition of good map. And if I replace this, essential supremum by just supremum, then I'm just going to say that it is absolutely good. Okay, and you should think about polynomials with respect to Lebesgue measure as one example. And in fact, in today's talk, we are going to show that a certain kind of functions are good, and that's the main kind of that's kind of one of the main things that we are going to talk about. Okay, all right. Any question? Okay. So let me try to define friendly and then give some examples. So first of all, it has to be Federer, which means if you take a ball of radius, so let's say x, take x in the support of mu, so mu friendly, and then take a ball of radius r and a ball of radius, let's say 3r. And then Federer means that the ball of radius 3r, the measure of that divided by the measure of ball of radius r must be bounded above by some constant d. And if you change 3 to any other number, then d may also change. But if you have this 3, then this d does not depend on r. And then it has to be non-planar, which means that so non-planar means, as it sounds, that you cannot, it is not supported on any affine subspace. So if you have any affine subspace L, then the measure of that must be 0. So L is an affine subspace. And then the last one, which is the most important one in what we are going to talk about. So any affine map. So affine maps means like you can take x going to C0, C1, X1, Cn, Xn. So this kind of maps must be C alpha good with respect to mu. Then we call that mu is decaying. So this is the definition of decaying. And if I change, of course, from good to absolute good, then you would have here absolutely decaying. Okay, you can also think about this last decaying condition as if you take, so let's say this is your open set, and you take any ball that is supported on mu, and take any affine line, let's say L, and then you look at the epsilon neighborhood of this line. So this function x going to the distance from x is an affine map. So basically what I just said before is same as saying that these maps are in particular C alpha good, which means that mu of B so this is B intersected with L epsilon. So this part here, this is L epsilon, that divided by the measure of the ball must be less than epsilon by the supremum norm, so that is just DL. So depends on whether you are asking C alpha or absolute, just decaying or absolute decaying. This would be the denominator would be the supremum or absolute supremum, essential supremum. Okay, so these last two things are same. Okay, so this is the definition of friendly measure, and also absolutely friendly if you have absolutely decaying. Now, what do we do with this? So the theorem that I stated here says that whenever mu is friendly, then mu is extremal. That means what variable, it behaves like the Lebesgue measure. Okay, all right. So now what is the question? The question is, so let me try to write a diagram. So you have this friendly measure. So what are the examples? And you have a strict definition of absolutely friendly. So Kleinbock-Margulis and Kleinbock-Lindenstrauss-Weiss work shows that, okay, so you can just take Lebesgue measure, that would be friendly. And then you can also take push forward by like f star of lambda d, where f is a map from open set of Rd to Rn. And if is not flat, then it would be friendly. And you can also, okay, so in fact, this Kleinbock-Lindenstrauss-Weiss paper also showed that if you take nice fractal measures, so I'm not going to define like what are the properties that it should have. But HS is supported on a nice fractal measure, so it should satisfy open set condition, and also it should be irreducible. Then this is actually absolutely friendly. Okay, so all of these are in reals. And then also they show this result, Kleinbock-Lindenstrauss-Weiss, that if you have now everything on the left-hand side, but replace the Lebesgue measure by fractal measure. So F is open set of Rd to Rn, not flat, and maybe also assume that it's not singular. Then F star of mu is friendly. Of course, mu is absolutely friendly. Okay, so let me just point out what is the situation in case of QPN. So in case of QPN, this left-hand side box is done by Kleinbock-Thomanov. This is also same as real case almost. The left-hand side is not same as real case, but the proof of the fractal measures being absolutely friendly are almost same. But then this result that if you have an absolutely friendly measure, and if you take the push forward under a nice map, it's not flat and in fact not singular, then the push forward is also friendly. That was not known, and it was in fact a conjecture. In case of QPN, it was a conjecture by Kleinbock-Thomanov. And in today's talk, I'm going to talk about that. Okay, any question? Okay, so let me write down our result. It's exactly what I just stated in the box here on right-hand side. Okay, so this is a work with Victor Beresnevich and Anish Ghosh. So we proved, so let me just write down the theorem. So F is U subset of QPD to QPN, absolutely friendly. F is non-singular and non-flat. Then F star of mu is friendly. Okay, so this is the conclusion in the box. And as I said that it was already proved that if you take any friendly measure, then it is extremal. So in particular, it shows that F star mu is also extremal. And that was a conjecture by Kleinbock and Thomanov.
Sorry, I missed something. So when F is called friendly, you said F is absolutely
no,
friendly.
so I said mu. Okay, so I meant, sorry. Yes, there should be mu is absolutely friendly. Thank you. Okay, so there are many consequences of this this theorem. So let me call this as Theorem A. So as I said that it implies, so corollary, let's say corollary eta, that under the same setup, as Theorem A, then F star mu is extremal, which means F star mu of BWA is 0. But you can also restrict yourself more, and you can actually just take a function instead of from QPD to QPN. You can also say that the function is actually flat. So Theorem C. So F is U subset of QPD to L. L is an affine subspace. Mu is absolutely friendly here. But F is, all the F is inside L, but F cannot be inside any proper affine subspace of L. So in some sense, F is non-flat inside L. Then F star mu is extremal if and only if L is extremal. Meaning if whatever happens in L will happen also in F star of mu. Okay, and then there are more applications. So this would be an upcoming theorem. Okay, let me not write it as let me not write it down, but it has application in absolute weaning of badly approximable vectors on analytic curves. So basically what I'm trying to say is that whenever you want to use quantitative non-divergence with respect to fractal measures, you need to use an analog. In case of QPN, you need to use this kind of theorem where it says that if you push forward by a nice function of a fractal measure, still the f star mu is nice. Okay, and I should point, I should also say here that when you work with things like this, where you have f star mu, where you want to show that f star mu is extremal, as I said that it was started with the work of Kleinbock and Margulis, where they use two things. One is Dani correspondence, and another is Dani's quantitative, more extension of Dani's quantitative non-divergence. So in the Dani correspondence, while showing that it's extremal, you only need one direction of Dani correspondence, meaning that you need that, okay, if you have a number theoretic set, and that is inside some, that implies that there exists a flow which goes to cusp at a certain way. And then you basically find the measure of that particular set in the homogeneous dynamics part. So you only need one direction. But when you prove something like this, you need both direction of Dani's quantitative non-divergence. And in case of QPN, Dani's correspondence that we have seen several times is not so straightforward. And I will briefly, so how much time do I have? I guess more 20 minutes.
Yeah, 20 minutes.
Yeah, so maybe I can just say one or two words about that. So I will just do a very simple case. Okay, so let's say Y is in QP. Then how do you embed? So in case of R, what you do is that you look at UY, where UY is 1Y 0, 1. Now, in case of QP, as I mentioned in the beginning, that you have to have the height with the denominator and the numerator. So that is one thing. Another thing is that in case of p-adic Diophantine approximation, you have one norm to be p-adic norm, and then the second norm is infinity norm. So of course, you cannot just work with SL and QP, and moreover, there is no cusp. So you cannot, you don't have any possibility of going to infinity. So in case of QP, what Kleinbock and Tomanov did, and they did only one side, which is that they embed this inside SL to QP cross R. So UY actually has two coordinates. So the p-adic coordinate has the usual upper triangular. And then in the infinity part, you just have identity. And then the GT flow, they had slightly more complicated, but I'm just writing very simplified GT. So let's take GT to be just p to the power minus t0, like this one in the p-adic part. And then in the infinity part, you can just take p to the power minus t by 2, p to the power minus t by 2. Okay, so now this is a flow inside. Now you can think about them as a flow inside the homogeneous space SL to QP cross R mod SL to Z1 over P. And then usually, like in Dani correspondence, what you would expect is that, okay, you start with Y to be like some W eta, where eta is the exponent, and W eta is the usual Diophantine approximation set that comes from the number theoretic part. And then you have an if and only if with, like, let's say G delta. So delta is the length of the shortest vector in a lattice. So there must be a sequence Tk going to infinity such that delta GTK Uy square is less than e to the power minus delta Tk. So there exists a delta. And you may expect that, like, in the real case, there is a correspondence like this. Unfortunately, in the p-adic case, you don't have a correspondence like this. And the reason is that on this side, you are doing approximation with Z, but here you have the lattice to be Z1 over P, right? So you may not expect to get back, like when you go from dynamics to number theory, you may not get approximation in Z. Okay, so in my PhD thesis so in one of the papers which came out of my thesis with my supervisor, we studied this problem and we showed that, well, this doesn't happen. But then Y is in some W, like some another set, which we denoted as W eta W tilde. And what is that? That is basically something like this. So we consider this kind of approximation. So Q naught plus Q dot Y P and then less than. This is more complicated than the usual one, but then this is more suitable with the homogeneous dynamics. So this happens for infinitely many Q and Q naught. So this is our Q tilde, but this is not in Z, but this is in Z1 over P square. So this is very complicated, but then the point is that it's kind of giving you another way, like there is no way that you cannot consider this kind of approximation and say that that suits with the dynamics, and then you have to convince that you are not doing something very weird, but you have some relation with the one that people study. So we showed that even though what you start from, you don't end up to the same set, but when you consider Diophantine exponents, then they match. But in case of, for instance, singular vectors, you won't have such a thing. Anyway, so I just want to, I don't want to talk more about this, but I just wanted to say that, like, in case of p-adic Diophantine approximation, the dynamics and the number theory, they do not talk to each other very well many times. So then you have to maybe, they may produce some different kind of Diophantine approximation. Okay, anyhow,
can I ask
so
a question? Is there a necessary and sufficient condition for the dynamical statement?
yes, so when you consider Diophantine exponent, then what we showed is that W tilde of eta is subset of W, the usual W, but not eta, but eta minus delta for every delta greater than 0. Okay, so that basically tells you that even though you don't get back to the same thing, but since you are allowed to take delta to be anything, then that means that the exponents are same. So when you talk about variable approximable, then it's fine. Then you have a correspondence.
Thank you.
Can I also ask a question? What about the badly approximable case?
Right. Even for badly approximable case, so as I said before, like in this ongoing work where we are, okay, so I think there is a lag with what I'm saying and my slides moving, but yeah. So yeah, here in this work where we prove Theorem D, we actually started with the dynamics, like the badly approximable definition coming from dynamics, and then we showed that actually same as the Diophantine, like the number theoretic definition. But if you take singular, then it's not the same. Or if you take uniform approximation, then they are not same. Okay. Okay, so let me, so this is just, this is something I wanted to mention because I said that when you want to prove for affine subspace, that if the affine subspace is extremal, then the push forward by fractal measure, like if the function is inside the affine subspace in a non-flat manner, then f star of mu is also behaves like the affine subspace. In that case, you need to have a correspondence. Okay, anyhow, so let me go back to Theorem A. Yeah, I'll just okay. Yeah, Theorem A. So here we want to prove that f star of mu is friendly. And okay, I said that there are three definitions of something being friendly. So it must be doubling, it must be non-planar, and it must have some decaying condition. And it turns out that the most difficult condition to show is the decaying condition. Okay, so this is the proof in so we are trying to, so I'll try to show that why the proof in real case doesn't work in case of QP, and how one can possibly approach. Okay, so okay. Right. So what is that we want to show? So so this is our goal. Want to find conditions on G. G is a function from a ball of QP to QP. Actually, we can do it for a ball in QPD to QP, but for now, I'm just going to restrict from QP to QP. And always the measure that I'm working with is absolutely friendly, which means it's doubling plus absolutely decaying. Okay, then you want to find the right conditions on G such that you can say that G is absolutely good on B. Okay, so I'm actually hiding a lot of details here, but what I'm trying to say is that you want to find an uniform condition such that whenever G satisfies those conditions, G must be absolutely good. And the condition, the constant that appear in this condition should determine the goodness of the functions G. Okay, so how did Kleinbock and Lindenstrauss prove in case of real? So they used mean value theorem again and again. In case of real, there is no mean value theorem. And we are working with any CL function in case of P, in case of QP. Okay, so this is real. Okay, so in the QP case, I must first mention that what is the definition of CL function, right? So okay, so if you take a function from QP to QP, then you can define P. So you can obviously define differentiability as you do in case of real, but I want to define even a stronger definition. And even then there is no mean value theorem, okay? So let me write phi1 of f. This is called the first difference quotient. So this is defined on, so if f is defined on QP, f is a function from QP to QP. Let's say the domain of f is actually an open set of QP. Then phi1 of f is defined on U cross U, but not on the diagonal. Okay, so the definition is this. This is a function on two variables, and this is just f of x minus f of y divided by x minus y. There is no problem in defining such a thing. But then the definition of C1, f is C1 if you can extend it to whole U cross U. So limit phi1 f xy equal to phi1. So if this happens, xy going to a comma a, then you call that to be f to be C1. But then you can also define phi2, phi3, and so on. And as you go, the domains will increase. The size of the domains will increase. Okay, now how to? So let me give one example. There are several occasions where they used mean value theorem, but let me start with a very simple lemma in case of R. So I'm just going to write it as lemma R, and this is from Kleinbock-Lindenstrauss-Weiss. And you can also like try to prove it in very simple case. It's just like it's a very straightforward application of mean value theorem. So you take B to be a ball. Inside U is an open subset, and let's say F is CK map, CK in the usual sense in case of R. And then you can show that infimum of Fk on this ball is less r to the power minus k, the supremum norm of F on the ball. Okay, now this is kind of the proof, like if you have, let's say 0, 2, you are basically saying that f of a plus 1 minus f of a is some f prime of c, and that's how you prove this in case of even higher fk. Okay, now we cannot do that in case of QP, but you have this this function phi1 and phi k, and it has this definition. So you can just use the definition and get something, but that something is weaker than what you get from the mean value theorem. But let me just write that down. So let me write it as lemma QP. So we could prove that infimum of pk of f less r to the power minus k. Okay, and as I said, that phi k is this thing is a function on a large set. So there is no, like, when you are talking about infimum, it may not be attained in the diagonal, right? So this could be really a weaker lemma than in case of R, because this may not be attained at something on the diagonal. Okay, but let's say we just try to work with what we have in case of QP. Okay, so in KLW, they say that, okay, if there exist two constants, small s and capital S, such that the function g, so b to r, such that it has two properties, infimum of gk is greater than, so let's say r to the power minus k, this, the k derivative is greater than r to the power minus k, and then the supremum of all the other all derivatives is, so this less and greater are determined by small s and capital S. Then G is C alpha good, and this C and this alpha will be determined by the small s and capital S. Okay, I'm not going to write down very like explicit things, but this is what they proved. Okay, now as I said that I don't have such a like strong theorem as in case of reals. So let's say naively, what you would do that you have this phi k. So let's just try to imitate their proof and see where we fail. Okay. So maybe since we don't have, it's not a great idea to like use gk, the k derivative, but maybe we can use phi k, right? And so let's say I have something like this as my condition. And sorry, so this is okay. And then let's say I want to conclude. You cannot, because so if you try to see the proof is that basically like you have the set that you want to, okay, this is your set. So you want to prove that if G satisfies these conditions, then G is C alpha good. So maybe you can try to prove it by induction. So maybe you can show that G prime, the first derivative, also satisfies these two properties, and that's not very hard to see that. Like you can put G prime here, and then G prime most likely satisfy these two conditions for k minus 1 instead of k. And then you conclude for G prime, and then you show that, let's say this set is the one that is, so you want to like prove something like this. So this is the set X in B, G of X less than epsilon. So this is EG. So let's say you take EG prime and you apply the induction hypothesis and you show that this set has measures small. And then the other parts, you use some local argument that there the derivatives are large. And then since this is a basic OV space, you can bound by the, there is a finite number of, if you take the measure, then there should be a finite countable, what is it called, multiplicity. Okay, so basically what I'm trying to say is that the proof goes by induction, and the proof uses that G prime should satisfy these two properties. And I just write down, okay, how much time do I have, or I'm almost, okay, maybe I'll just take 2 or 3 minutes. Is that fine? Yeah. Okay, so so they show that infimum of GK. So this is by hypothesis R to the power minus K GB, and then this is infimum of same thing G prime K minus 1 is less R to the power K minus 1 G prime B, and this is by the previous lemma R. Now I just want to point out that this very simple step where you have that G prime of K is GK is same as G prime K minus 1. That is just not true in case of what the functions that we are taking, phi k. Okay, so we don't have, so basically if you take P2 P2 of f prime that is not same as, or let's say P2 of f that is not same as P1 of f prime. Okay, in fact, that is sum of two such functions. So basically, this is true. P2 of f x, y, z is phi1 f prime. Sorry, this is. Okay, anyhow, I don't want to write it down, but basically, this doesn't work. Okay, so the idea is that these two conditions, the analogous same conditions, are not good enough. We need an extra condition. So condition 1, let's say, which is that you should have P, like a chain of inequalities to be satisfied. So I'm just going to write down the first two, but maybe you can imagine what would be, like you would have a chain of equations that need to satisfy it, and then you can like use their kind of methods and show that the conclusion is true. But then we have an extra assumption, but we don't want our last theorem to have such an extra condition. So the idea is that first you show that this abstract theorem is true, and then you show that polynomials satisfy this condition, these three conditions. And then you also approximate these kind of functions of the polynomial and the original function uniformly. And then the kind of function that you are working with will also satisfy these three properties. And I think I want to stop here. Sorry, I think I took 2 minutes extra.
Are there any questions, comments?
So I want to ask that whether this proof is independent of the characteristic of the field. In other words,
Yeah, this would work even for function field. We are not using any characteristics zero property of QP. We are using altimetric property, but we are using Basikovich, that the QP is Basikovich and so is function field. So as long as the altimetric space is Basikovich, these things will work.
Okay, thank you. Can you hear me? So do you get a better or a worse alpha in this argument? I mean, in the original paper, there was a discussion about the optimality of alpha, and I'm curious whether this new proof does better than, depending on, in some regimes, there were two proofs, one due to Kleinbock-Margulis and one in KLW paper of C alpha good of for certain maps, and in some regime KM get a better alpha, and in some regime KLW get a better alpha. And I'm asking whether your new proof might do a better job and get a better alpha in some cases.
No, I don't think it gives a better alpha. It may give like 1/2 of the previous alpha, but that's not like really better.
Okay, thank you.
Any more questions? Okay, if not, then let's thank the speaker again for this wonderful talk.
Thank you. And happy birthday, Professor Dani.